When you're dealing with enough stored energy to level a building, you absolutely need a rulebook. So today, we're going to break down the most important one, the ASME U1 scope. Seriously, understanding its boundaries is the very first step to making sure any project involving pressure is built safely and correctly.
So let me ask you this. What in the world connects a fire extinguisher, a massive power plant, and a submarine? I mean, it sounds like a weird riddle, right? But believe it or not, they all rely on the exact same piece of core technology to function, the pressure vessel.
So what exactly is a pressure vessel? Well, the official ASME code keeps it pretty simple. It's just a container for the containment of pressure, either internal or external. That pressure could be pushing from the inside out or even from the outside in. It's a really simple definition for a powerful and, let's be honest, potentially dangerous piece of equipment.
Right. Containing all that energy means that with great pressure comes, you guessed it, great responsibility. You can't just weld one of these together in your garage and cross your fingers. That's why there's a detailed and incredibly important rulebook that governs exactly how they're designed, built, and tested. So in this explainer, we're going to walk through the very starting point of that rulebook, the U1 scope. We'll look at what it covers and, just as important, what it doesn't. We'll get into the key limits you have to know and why getting this first step right is so critical for any project.
All right, first up, the big idea. And it's really simple. When you're dealing with the kind of stored energy that can cause serious damage, having a clear set of rules isn't just a good idea, it's an absolute necessity for keeping people safe.
And that brings us to the rulebook itself, the ASME Boiler and Pressure Vessel Code, specifically Section VIII Division 1. Just think of this as the definitive guide. It's the industry standard that engineers and manufacturers all over the world use to make sure every single vessel is built to the same high standard of safety.
Now, the code itself uses some pretty formal language, but its entire philosophy really boils down to three simple ideas. You've got your mandatory requirements. These are the absolute must-dos, no exceptions. Then there are specific prohibitions. Those are the don't-evers. And finally, you have non-mandatory guidance, which are basically the good ideas, the highly recommended best practices.
Okay, so to use this rulebook the right way, you have to understand how it's put together. It's not just some random list of rules, it's actually organized in a very logical way.
See, it flows from the general to the specific. It all starts with subsection A, which lays out the general rules that apply to literally all vessels. Then, you move to subsection B, which gets into the nitty-gritty of how you build it, the rules for things like welding, forging, and brazing. And finally, subsection C details the requirements for the materials you're using, everything from carbon steel to fancy alloys. It's actually a beautifully logical system.
Now for a really crucial point that sometimes gets overlooked, knowing what the rulebook doesn't cover. I mean, understanding the scope is all about knowing the boundaries, and that includes what falls outside of them. This is every bit as important as knowing what's in.
So, the first big category of things that are excluded are items that simply have their own different rulebooks. These things aren't just ignored, they're just covered somewhere else. Stuff like piping systems, pumps, and valves, they all have their own dedicated ASME codes. It's all about making sure you're applying the right set of rules to the right piece of equipment.
The next set of exclusions is all about risk. The code basically recognizes that some vessels are just too small or operate at too low a pressure to really pose a significant danger. So, for example, vessels running at less than 15 psi, or tiny ones with an internal diameter of 6 inches or less, they fall outside the scope of these particular rules.
And then you get into the really specialized cases. For instance, vessels designed for people to be inside them, think submersibles or decompression chambers, are excluded. And why is that? Well, because the safety standards for those are so incredibly extreme and unique that they need their very own, even more stringent, set of regulations.
So we know what's in and we know what's out, but where's the actual dividing line? Let's talk about the hard numbers and the physical boundaries that define exactly where this code's authority begins and where it ends.
There is one number that really defines the upper limit for this part of the code: 3,000 psi. Let's dig into what that actually means. To put that into perspective, 3,000 psi is more than 100 times the pressure in your car tire. It's a lot. Division 1, the rulebook we're focused on, is designed for vessels operating up to that limit. Now, you can absolutely build vessels for higher pressures, but they fall under different rulebooks like Division 2 or 3, which have their own, much more demanding requirements.
Okay, so we've got a pressure limit. That makes sense. But what about the physical limit? If you're looking at a big, complex system,
Where exactly does the pressure vessel part stop and the piping part begin? Well, the code is super specific about this.
And here they are, those exact boundaries. For a welded connection, the vessel's jurisdiction ends at the very first weld. For a screwed pipe, it's the first thread. For a bolted flange connection, it's the face of that first flange. This is so important because it defines the exact handoff point where the rules of this code stop and another code, like the one for piping, takes over.
Okay, so we've walked through the rules, the structure, the boundaries, all of it. But why does all this technical detail actually matter when you're on a real-world project?
This quote from the code itself really gets to the heart of it. Think of it this way. The ASME code provides the technical rulebook, but it's the local, state, and federal laws that turn that rulebook into a mandatory requirement. An inspector is going to use this exact scope to figure out which laws your project has to follow.
So you see, understanding the UN scope isn't just some academic exercise. It's the absolute first, non-negotiable step in any project that involves a pressure vessel. Getting it right ensures safety, it guarantees you're complying with the law, and it really just sets your project up for success from the very beginning. Answering that question, is my vessel in or out of scope, that's where it all begins.
So, we've defined the clear lines and boundaries that the code sets out, but that leaves us with one last thought. What happens in the gray areas? What happens when your project is operating right on the very edge of these rules? Well, that's where true engineering judgment and deep expertise really come into play.